This is my third lecture in the discussion of concept of stress. Uh, this lecture I'll start with uh, the discussion on Mohr circle in 3D. In my previous lecture, I have given some introduction of the 3D Mohr circle in my MATLAB demonstration, but in this lecture, we'll see how mathematically we can get those equation of circles. So to start with, let us think again the stress tensor defined with respect to the principal direction as the basis vector, so that we uh, have the diagonal matrix to represent the stress tensor sigma, and the diagonal elements will be the eigenvalues or the principal stresses sigma 1, sigma 2, and sigma 3. And with respect to uh, that stress tensor definition, we'll now see how the normal stress and the shear stress on a particular plane can be defined. So we'll define one arbitrary plane with respect to that principal directions as the basis vector. So our basis vectors are n1, n2, and n3 hat. So and the arbitrary plane will be defined using three components m1, m2, and m3 with respect to those basis vectors. So then m hat will be as m1 n1 hat plus m2 n2 hat plus m3 n3 hat. So then we know the formula to get the normal stress and shear stress magnitudes. So the normal stress is m transpose sigma m, which gives this relation, and then the square of the shear stress magnitude is defined as m transpose sigma m minus the magnitude of the normal stress square, and that will give this expression. Alright, then we have one constraint equation, which is m1 square plus m2 square plus m3 square equal to 1. So we have three equations where you can see all those equations. We find the squares of the components m1, m2, and m3. So we now can solve these three equations for this, and we will be able to find what are those solution uh, for m1 square, m2 square, and m3 square in terms of sigma m, tau m, and sigma 1, sigma 2, and sigma 3. So you can use any symbolic symbolic math package like Mathematica or Maple to solve this equation. So after solving, what we get is written here. So if we solve this three equation, we will get the solution as this: m1 square equal to tau m square plus sigma m minus sigma 2 times sigma m minus sigma 3, that is in the numerator, and in the denominator sigma 1 minus sigma 2 and sigma 1 minus sigma 3. So this actually has a very nice form. It's not that difficult to remember. So you can see in the top, in the numerator, you'll have tau m and sigma m, and in the denominator, you'll have the sigmas. Okay, sigma 1, sigma 2, and sigma 3. And for m1 we'll have sigma 1 in this place, sigma 1 in this place, and for m2 we'll have sigma 2 here, sigma 2 here, and then the others will be just subtracted from that sigma 2. Sigma 2 minus sigma 3 and sigma 2 minus sigma 1. Similarly, in the top here tau m square plus then sigma m minus that sigma 3 and here sigma 1. So it is same for the other two cases also. And we know that this is the square of uh, the component m1, m2, and m3. So the squares should be greater than equal to 0. So we get one inequality. And now we'll see closely what these equations are actually giving us. So here let us again consider that we arrange this values of the sigmas such that sigma 1 is greater than sigma 2 and greater than equal to sigma 3. And then we know from the first equation the denominator is positive, so that means the numerator also will be positive, so that's why we get this equation. But for the second one you can see sigma 2 minus sigma 3 is positive, but sigma 2 minus sigma 1 is negative, so altogether it is negative. That's why the numerator also will become negative to make it greater than 0. uh, but for the third case you can see this is negative, sigma 3 minus sigma 1, and sigma 3 minus sigma 2 also will be negative, so 2 negative makes positive, so the numerator will be also greater than equal to 0 for this case as just for the first case. So you get two equations as greater than equal to 0 and one as less than equal to 0. So now we'll try to manipulate these equations a little bit and see what we get. Let us take the first one. So tau m squared plus sigma m minus sigma 2 times sigma m minus sigma 3, and then you just expand this equation, and then we add these terms to these two terms, and then we can see we can rearrange these terms, and we can get an equation in this form: tau m square plus sigma m minus sigma 2 plus sigma 3 by 2 whole square is greater than equal to sigma 2 minus sigma 3 by 2 whole square. So this, you can see this equation similar to equation of circle. It is, you can see, think of sigma m as the x-axis and tau m as y-axis, then it is y square plus x minus some xc is the center, xc square greater than equal to r square. So x minus xc square plus y square greater than equal to r square. So if it is equal, then it is a circle, and if the greater than equal to sign will say that the points x and y will be outside this circle. Okay, sigma 2 minus sigma 3 by 2 will be the radius, so it is, and the sigma 2 plus sigma 3 by 2 will be the center of this circle, and the points tau m and sigma m will be outside or on the periphery of the surface or of the circle. Okay, so similarly from the other two equations we will get these two inequalities, and these two also are equation of circles, and this in this the first one, say the center will be sigma 1 plus sigma 3 by 2, and the radius is sigma 1 minus sigma 3 by 2, And you can see because of this less than equal to sign, the tau m and sigma m will be inside that circle. And whereas for the third one, we have the center sigma 1 plus sigma 2 by 2, and the radius is sigma 1 minus sigma 2 by 2, and the points will be outside this circle. So that means if I have sigma and tau axis represented in this way, x and y respectively, then the principal stresses sigma 1 here, sigma 2 here, and sigma 3 here. Here we have assumed there as positive numbers, but it can be negative. So this circle will shift to the negative axis of the sigma, but the pattern or the behavior will be same. But here sigma 1 will be right side, and then sigma 2 will be middle, and sigma 3 will be left side, because we have assumed sigma 1 greater than sigma 2 greater than sigma 3. And then we'll, based on this values, we can form 3 circles. One circle with the sigma 1 and sigma 2, and then another circle with sigma 2 and 3, and the bigger circle will get using sigma 1 and sigma 3. And we can see from the equations that the sigma and tau, that is the normal stress and the shear stress at any given plane, will lie within these 3 circles. So inside the bigger circle and outside 2 smaller circles. So that's very interesting observation, and there are different various use of this interpretation in different other mechanics, but I will not go into details of those things, but you can just take a note of this thing, that there are 3 circles formed by the 3 principal values, and then your the point sigma and tau will be within these 3 circles. And if you remember my MATLAB demonstration, I showed this thing, but one difference you can note here, that I got semicircles instead of full circle, but here we are getting full circle. The only reason of this two difference is in MATLAB, when I found out the shear stress magnitude, I remember I used a square root function, SQRT. So SQRT will give always a positive number, whereas the tau, when it is tau, if it is square root of 2, will get 1.414 always, but the solution can be also minus 1.414. So MATLAB will not compute that. So that's why in MATLAB we get only positive side of the y-axis, but in principle that can be a full circle. Okay, so that's what we see here. And then now we can see from this diagram the maximum shear stress we get as the radius of the bigger circle, which is sigma 1 minus sigma 3 by 2. And if you remember the extremum values of shear stresses we discussed, so that's what we got as maximum shear stress value. And then the normal stress associated with the maximum shear will be the center of this circle, which is sigma 1 plus sigma 3 by 2. That's what also we have got earlier. Okay. So now, before going to this octahedral stresses, let me show you something again related to this Morse circle. So if you remember in your first year mechanics course, you encounter the stress transformation and the 2D Morse circles. So the stress transformation, we have probably you have done the derivation of the sigma and tau in a different plane by using a uh, balance of forces, a Newtonian kind of approach we have done. And I will show you how this tensorial approach can be applied to get this same expressions. So let us go through this like additional PDF, which I can also send you. Let us say in this there is the original stress state defined with respect to the x y coordinate system as sigma x, sigma y, and tau xy. So this is my uh, the stress tensor with respect to xy system. In figure it is shown in black color. Then I have a prime system which is x prime and y prime, where is the x prime and the angle between x prime and x is theta. Then if I want to find out the stress state, the transform stress state in this new coordinate system x prime y prime, then here in this phase where the normal is n hat, we'll have sigma x prime and tau x prime y prime as the two stress components, and along this normal n hat perpendicular, so it is the perpendicular to the n hat, we'll have stress components at sigma y prime and then tau x prime y prime. So now let us see how we can get using our that matrix equations. So here n hat is defined as cos theta sin theta 0, and n hat perpendicular is defined as minus sin theta cos theta 0. And then we know the traction vector on that particular plane of n hat will be sigma n, which is giving this equation. This is the traction vector, 3 components. And then to get the normal stress component on that plane, we have to have a dot product of traction vector and the n hat. So if you do that, it is n hat transpose t or t transpose n hat, both will be same. And then it is this matrix multiplication, two column vectors, one transpose and another the column vector. And if we just rearrange this equation, we will see that we get sigma x prime as sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. So if you remember, you have got this relation earlier. Similarly, if I want to find tau x prime y prime, then the traction vector has to be dotted with the n hat perpendicular vector, because it is the component of the traction vector along n hat perpendicular. That's what the tau x prime y prime is. So then if we do that, then we will see that the tau x prime y prime is coming out to be this. So this is, in my opinion, it's not a very difficult formula to obtain. So if in case you don't remember whether it is plus, minus, or sigma x minus y or sigma y minus x, something like that, so you can just do a 1 minute small calculation and you'll be able to find this formula. Even you can obtain the sigma y prime by taking this sigma and then uh, n perpendicular as the traction vector. You'll be able to get say n perpendicular as the normal vector, and then you find traction vector in that plane, and then get the component of the traction vector along this n hat perpendicular. We'll be able to obtain the sigma y prime. So you can do it on your own. And another thing also you can do, if you want to find the expression of the principal stresses, so you know that these are the eigenvalues of this equation. So you just find the eigenvalues of this sigma matrix. So sigma x minus lambda, tau xy 0, tau xy sigma y minus lambda 0, and 0 0 minus lambda. So you just find the determinant and set to 0. You'll get three values of lambda as the root of that characteristic equation. One lambda, the one root of lambda will be 0. Another two root will give you the principal values of uh, this 2D stress stress state, and you will see that the formula what you will get here will be exactly same uh, what we got in your first year course. All right, so having said that, let me again go back to the original PDF. Here now we'll discuss what is the octahedral stresses. So octahedral stresses nothing but some stress components obtained in octahedral planes. Okay, and the octahedral planes are defined uh, as as the planes which makes equal angle with each of the three principal directions. So here you have to make a specific note to this definition. So I saw people, the students make mistake that they think that it is the plane which makes equal angle to three arbitrary basis vectors E1, E2, E3, but it's not. It's the N1, N2, N3 planes or the basis vectors defined as N1, N2, N3 as the principal directions. So with respect to that basis vector, if I find a plane which makes equal angle to these three uh, the coordinate system or the basis vectors, then that plane will be called as octahedral plane. Why octahedral? Because octa means 8. You will see that we will get 8 such planes because principal directions will be along n1 and also along minus n1. So both are the principal direction. So considering that positive and negative side of n1, n2, n3, we will have total 8 octahedral planes. So you can see here from this picture. So there will be 8 such planes, and on that plane you will have both normal and shear stress components. So that will be defined as sigma oct and tau oct, sigma octahedral and tau octahedral. So we'll see what will be the mathematical expressions of those normal stress and shear stress with respect to the principal values sigma 1, sigma 2, and sigma 3. So here you can see the M, the equation of plane for the octahedral plane will be uh, m1, m2, and m3. They will be equal, and this, the values will be plus minus 1 by root 3, because m1 square plus m2 square plus m3 square will be 1, and then 3 m1 square will be equal to 1, and m1 will be plus minus 1 by 3, and that will be equal to m2 and m3. All right. So then if we try to find sigma octahedral, we know that that's the relation for arbitrary plane m1, m2, m3. Then if we put m1 squared equal to 1 by 3, then so as m2 square and m3 square, we'll get this relation. So it is the stress that yeah, so it is if we try to find with respect to norm the principal stresses, then it is sigma 1 plus sigma 2 plus sigma 3 by 3. But you make a note here that the sigma 1 plus sigma 2 plus sigma 3 is nothing but I1, which is actually an invariant. So if, that means sigma oct is I1 by 3, which is also equal to sigma 1 1 plus sigma 2 2 plus sigma 3 3 with respect to any arbitrary basis vector. So it is always the sum of the diagonal matrix, sum of the diagonals by 3. Okay. So then we know also that the tau octahedral square is defined in this using this formula, and then if we put these values of m's, we'll get some simplified formula like this. So this is also some relevant expression. If we discuss plasticity theory, this value tau actually has some significance, but I'm not going to the details again here. Just remember that this is the magnitude of the shear stress and the square of the magnitude of the shear stress uh, on the octahedral plane. Okay, and this there at as I mentioned, this also has relation with respect to this invariance. So similar the the shear stress tau oct also will have be expressed. We will have some expression with respect to the invariance I1 and I2 here. So sigma oct is only based on I1, but here the shear stress tau oct will be I1 and I2. So these are all expressions you can remember, but if you know one, you can get the other expression from that one easily. So anyone you should at least remember. All right, so now we'll move to the definition of hydrostatic and deviatoric stress tensor. So for a stress tensor, sigma Isaac can be split into two component tensor. One is the hydrostatic stress tensor, another is the deviatoric stress tensor. Hydrostatic stress means the stress uh, mm, is like the stress state is having same stress values in all direction. So you can think of like one small cuboid placed in the inside the water. Then the small cuboid will have same pressure or from all along the uh, all along like all from all directions. So that means it will have same stress values. So, you can think of pressure as normal stress. So that's why this name as hydrostatic is a static pressure we obtain when we place something inside the water. And mathematically, we can define hydrostatic stress as sigma m, which is the sigma m times unit vector, because the stress is same in all three directions. So that is your and the magnitude of that stress is sigma m, which is nothing but the average stress. So it is sigma kk by 3, or it's I1 by 3. Okay. So you can see one also important observation that this matrix is a identity matrix. That means the eigenvalues will be eigenvalues of this hydrostatic stress tensor will be always sigma m, and the eigenvector direction will be uh, all possible 360 direction. So that means if we change to like any different coordinate system, the stress state will remain same. So it will be purely a hydrostatic kind of stress. So it doesn't depend on the coordinate system rotation. And then the remaining part will be the Debye-static stress tensor, so which is defined as S, which is sigma minus that hydrostatic stress tensor, and we will see this will be the expression of the Debye stress tensor, and which is in index form. It is written like this. So then the principal stress invariants of this Debye stress tensor will be J1, J2, and J3. And if we carefully see, the J1 will be the diagonal of the sum of the diagonals of this S matrix, which is actually 0. So the stress of this S matrix will be 0 as per our definition, but J2 and J3 will be non-zero. And then characteristic equation of this Sij is defined in this way. Here you can see one difference with respect to the sigma characteristic equation is here deliberately we have put minus sign in place of plus. So earlier it was sigma cube minus I1 sigma square plus I2 sigma minus I3. So, but here we are having S cube, then the second term will be minus S minus J1 S square, but J1 is 0, that's why it is not coming. Then it would have been plus J2S, but we are actually taking minus J2 here, and then minus J3. And so this minus the minus J2 we are taking because the J2 with this taking minus sign will have some positive number, and that will be used in the J2 plasticity theory. So to consider that J2 plasticity, it is taken as negative here. So there is no other reason. So because this J2 will have some significance, we'll discuss J2 plasticity. Now we also can see one interesting thing, that the eigenvalue of this Debye stress tensor will be just, you can go through this derivation, and you will see that the eigenvalues of the Debye stress tensor will be just the eigenvalue of the original matrix sigma minus that sigma m, the magnitude of the hydrostatic stress, hydrostatic normal stress. So it is they are related using. So if we know the eigenvalue of the original stress matrix sigma 1, sigma 2, sigma 3, then we don't have to calculate eigenvalues of this matrix. You just use simple calculate means using the normal procedure of calculating eigenvalues from a matrix. You can just use this equation, you'll be able to find it. And also we can see here with this example, this mathematical derivations, that the eigenvectors of these two matrices sigma and the S will be same. So eigenvectors or the principal direction of both sigma and S will be same, and the principal values or the eigenvalues will differ by this equation. So uh, they're different, but the eigenvectors are same. Okay. All right. So now there are this expression of J2 and J3 with respect to the principal stress variants I1 and I2. This is the relation you can remember. And the last topic of this is equation of equilibrium. So here you can see that if we consider the static case, and then even for dynamics also it will be applied. So we have to consider for equilibrium two governing fundamental equation. One is the conservation of angular momentum, which we have already considered while discussing the symmetry of the stress tensor. And now we can consider the second uh, fundamental equation, which is the conservation of linear momentum. And with that, you can see we'll get three equations by considering balance the angular sorry the linear momentum balance along E1, E2, and E3, and that with like this picture here you can see I have used the notation of sigmas a little different here because I mentioned because of the symmetry of the stress tensor. You can have either sigma 1 2 or 2 1 in this place, no issues. Similarly, this can be sigma 3 2 or 2 3. So here actually the plane is defined as the first index and the directions along the three basis vectors are the second index, but I think they're acceptable, no issues. And then we have considered incremental changes because we are considering a body which is under uh, differential or under non-uniform stress state. So the values in one surface can be different than the other surface, and there can be some incremental changes. So with that, if you just consider the force balance along these three directions, you will see that we'll get this equation. Sum of, let us say it is one direction, then sum of F1 is equal to MA1, and then you consider the forces coming due to the stress components. Stress multiplied the area on the surface will give you force, and then you have to consider one more term, which is the body force term. So F1 is the body force per unit volume. Body force means some simple example like gravity and all, so which acts over the volume of the material, and then the mass times the acceleration in the one direction. So if we simply simplify this equation, you'll get the equation in this form. Here rho is the density and F1 is the body force per unit volume. And then if we consider the linear momentum balance again along 2 3, you will get the other two equations. So these three equations combining is will be the equilibrium equation, and basically equilibrium equation will use this term for the case of statics actually. So when uh, the acceleration term will be 0. So this is the index notation of the equilibrium equation, and this is the vector notation of the uh, equilibrium equation. And when we set a equal to 0 for static case, we get this equation, and the this is the equilibrium equation. Okay, so if body has to be in equilibrium, so the relation of the stresses should follow these three equations. Okay, so that's a very fundamental equation. Sometimes like this equation will be needed for solving many problems related to solid and fluid mechanics. All right, so now we have these exercises. I will suggest you to go through these problems and solve on your own. If you have any doubt, you can ping me. I'll try to help you as as much as possible. And I'll also send you one assignment regarding the stress calculation that I'll give you a timeline. You can send me by like through emails, individual emails, uh, submitting that assignment. Okay, so I'll shortly send you this assignment to you. All right, so this is the end of our discussion in the concept of stress. In the next lecture, I'll be discussing concept of strain. Okay. All right. So, uh, thank you.